human-occupied submersible Alvin, the remotely operated vehicle Jason, and the autonomous underwater vehicle Sentry. Talk about some of the ways that these vehicles are used and a bit about how you can be a user of the facility, how you get access to these vehicles. We're going to have time at the end to have some questions and answers, but if you have a question during the presentation, I encourage you to type it in, and the staff at AGU is going to relay those questions to me so that we can make sure that we don't have any kind of misunderstandings or things that I don't cover in enough detail or too much detail during the presentation. So I'm happy for your interruptions. All right, so the Woods Hole Oceanographic Institution has a long history of deep submergence science, and I'm going to kind of pick it up at the time where we started using what I'd call deep submergence vehicles. But prior to this 50-year history, people were lowering cameras on wires and towing things along the seafloor. But in about 54 years ago, the deep submergence vehicle Alvin, the human-occupied submersible Alvin, was developed, and that kind of revolutionized the way that we do science in the deep ocean. It was supported in its development by the Navy. In fact, the vehicle is still owned by the Navy, and it was created as a kind of lightweight, flexible, small submersible that could be used for inspection of the seafloor, in particular related to wrecks of submarines, which at that time was, there were a few of them. So it was built by Woods Hole and was used primarily for science, and in the mid-1970s was recognized that this was a capability that the whole of the US research community could take advantage of. And so in 1974, NOAA, NSF, and the Office of Naval Research combined to create the National Deep Submergence Facility and provide this operational capability of Alvin for US researchers. In 1995, the facility expanded to include ROV Jason, remotely operated vehicle Jason. And in 2006, the autonomous underwater vehicle ABE was added to the facility, which was followed shortly after by Sentry as ABE was lost at sea. So over the history of the deep submergence facility and before, you can see on the lower left-hand side of the screen kind of the location of dives that have taken place. And we've covered a fair portion of the globe with these deep submergence vehicles, although you can see places where we haven't spent as much time, towards the poles, in the kind of higher latitudes where sea conditions are difficult. But over that history, we're approaching 5,000 dives for Alvin. This year, we're going to reach 5,000 dives for Alvin. Many of you are going to be participating on the cruise where that happens. We're approaching 500 dives for Sentry and over 1,200 dives for Jason. So it's provided the scientific community with a great deal of access to the seafloor. And the science that's come out of it, as well as the kind of, in addition to the science, the kind of societally important events that have come from using these vehicles are many. And I've put together a small list here. In the late 1970s, there was the discovery of hydrothermal vents in deep sea chemosynthetic ecosystems, bringing about a kind of fundamental change in the ways in which we understand life can exist on this planet. In the 1980s, Argo and Alvin were used to discover the Titanic, and the scientific value notwithstanding, this was a huge cultural event and really important for starting to communicate the importance of deep sea research to the broader world. In 2000, Alvin discovered the Lost City hydrothermal field, a fundamentally different type of chemical environment that existed on the seafloor. In 2010, both Sentry and Alvin were pressed into service in response to the Deepwater Horizon oil spill in the Gulf of Mexico. In 2009, Jason made the first observations of active submarine volcanic eruptions on the seafloor. In 2017, Sentry located the voyage data recorder for the El Faro cargo vessel that sank in the Atlantic. And all of these are great accomplishments and are really important to both our science and how we as deep sea scientists are viewed by the broader public. But I think that the most important thing that these vehicles have done and continue to do is to support basic research in the oceans, as well as integrative programs. The RIDGE program, the Margins program, IODP, Cascadia, OOI. These tools are a nexus for geologists, chemists, biologists, physical oceanographers, and a real asset to, I think, furthering our ability to do science in the ocean. And this list is not complete, and I think importantly, this group in particular of new users is gonna be the folks who are gonna add to this list. So I'm excited to be talking to you about the facility today. So as we go through the webinar here, I'm gonna talk about the different vehicles, but there's a couple of messages that I hope to get across, and so I'll just kind of say them now. First of all, these are your platforms for ocean research, by which I mean what you want to do in the oceans is going to control how these vehicles evolve and how their progeny evolves. So you are important to the process. These vehicles are constantly in a state of renewal, getting overhauled and modified, and it's based on what your science needs are that'll determine what those changes are. The other important point is that myself, as the chief scientist for Deep Submergence, as well as the managers of the vehicles, which I will give you their contact information, are always available to you to answer your questions, provide guidance, connect you with the right people to help you kind of develop your approach and plans for using these vehicles and carry you through the process of a science mission from kind of conception through execution. So please know that you're always welcome to reach out to me or any of these folks to help you understand how the vehicles work or what their capabilities are. So I'm going to start by giving a little overview of HOV Alvin, or Human Occupied Vehicle Alvin. This is kind of the celebrity of the National Deep Submergence Facility. It's probably the most well-known science submarine in the world. It is operated off of RV Atlantis. This is a global class ship that can support 24 scientists in addition to 30-some crew. The vehicle operates to 4,500 meters at present, and it goes down to the seafloor with 1 pilot and 2 observers. It has a payload of 400 pounds, so it can take 400 pounds of samples or equipment through that air-water interface. It's an extremely facile vehicle. It has 7 thrusters that allows it to move in almost any direction and be able to handle extremely kind of challenging terrain. It does a lot of the work on the seafloor with its manipulators. They have both a kind of a elbow joints and wrist joints, but also a shoulder joint so that they can rotate well out from the vehicle. And it's got 6, at present, 6 user selectable HD video and digital still cameras. Now, when you're using Alvin, kind of the vehicle safety systems and such are really important, but the spot on the vehicle that gets might get most of your attention is the basket that sits out in front of the vehicle. So you can see it here. It's changed a little bit from this picture, but it still sits right below the pilot's viewport out in front of the vehicle. And it's where you are going to store your tools and your equipment and bring your samples back. So it's the place where what you need to achieve your science lives. And I'm going to talk a little bit about the tools that are available to use with Alvin and that people have developed on their own to use with Alvin. In this image here, you can see the basket, as we call it, is extremely loaded with a pumping system and that contains dozens of bottles that are going to collect fluid and bring it back to the surface. So the types of tools that are on the vehicle, and it's pretty important to know what's available to you as a tool, so that when you're planning your science on the seafloor, you have the right stuff with you. Because once you're down there, obviously you have what you have. But some of the tools that are standard and available to any scientist who use the vehicle include, let's start up in the upper right, push cores. Those are kind of clear acrylic cylinders that you press into the sediment and pull up to recover sediment. Niskin bottles that can be tripped from within the sub to collect seawater from either at the seabed or in the water column or at the surface. Slurp systems or pumps that pull water and whatever material is there through a tube into a chamber and then filter that material so the seawater goes away as a way to collect animals that would otherwise be impossible to collect without damaging. You can imagine some snails, for example, grabbing them with a manipulator, you're going to crush them, but sucking them up with the slurp, you're going to collect a whole bunch and keep them in pristine condition. I'm going to skip over the top left for a second, but if we go down to the next row, there's a bio box. So these can be placed on Alvin. Animals can be put inside the bio box and isolated from ambient seawater so they can be kept in relatively cold bottom water that they were found in, which will help keep them preserved as well as possible on that trip from the seafloor up to the surface. Next to that is a temperature probe. Commonly, if you're working around hydrothermal vents, you want to know where the fluids are the hottest in order to collect samples, and this is a way to achieve that. A CTD, which as you do transects across the seafloor, you might notice a change in the fauna, which might correlate with a change in the water properties. A scoop net, which you can use to scoop up clams or mussels or rocks that are particularly fragile. And then the 3 remaining ones are tools that that scientists have built to use with the vehicle. So in the upper left, I have a hydrothermal fluid particle sampler. You saw that in that initial image of the basket. This is a sampler that was created by Dave Butterfield, and is a system for pumping and filtering hydrothermal fluids to collect samples and look at the chemistry of the fluids and the precipitates. This is an example of a device that basically takes up the entire basket. On the other end of the kind of technology spectrum, we have these microbial colonizers, which you'll recognize as, I guess they're called scrubbies, maybe, I don't know, dish scrubbies. And these are put out to, they have a lot of surface area for microbes to colonize on, and then recovered and the microbes are scraped off. So high tech and low tech, and then in another example of high tech, the IGT, or the isobaric gas tight sampler. This is basically a titanium tube or syringe that the fluids are sucked into and kept at their ambient pressure so that the dissolved gases can be analyzed back up on the ship. Now, to expand your capabilities on the seafloor for tools or samples that are larger than what can be handled on one of the vehicles, we commonly use elevators. So there's an image of an elevator here. This is basically a platform with some flotation on it. The platform is weighted so it free falls to the seafloor, and those weights are released to allow it to rise back up to the surface. So this is done untethered, but tracked with a USBL beacon. I don't know if you can tell, but I keep pointing at my screen, so I'll use this cursor instead. Not sure if you can see it. And what it is basically a deck that you can put stuff on. In this example here, some large samples of chimneys, I suppose, are being recovered, and they're larger than maybe could be handled on the Alvin basket with the other equipment that was on there. You can also use it to deploy large-scale experiments. In this case, a virus sampler from Rika Anderson, which is running a pump and collecting large volumes of fluid on the seafloor. The other benefit of setting up your experiment on a elevator like this is that you can, if it's the type that requires you to turn it on and off, you can turn it on. You can use the vehicle Alvin in this case to head off and do more work, and then come back and recover it later. So as I mentioned, these vehicles are in a constant state of renewal. Along the bottom of this slide, you can see how the profile of Alvin has changed through the years from the 1960s to its most recent upgrade, which was in 2014. The main component of this upgrade was a larger personnel sphere, the titanium sphere that you go into and keeps the pressure out. And some of the big changes that came with it were the addition of 2 new viewports. Viewports are your way to access the seafloor from inside the safety of the sub, and new ones were added that overlap the view that the pilot has. And this is hugely helpful because when you're asking the pilot to collect this sample or that sample, being able to look out and see what the pilot sees really helps that process move more quickly and efficiently. An additional thruster was added that gives Alvin some greater degrees of freedom in the way that it moves. The improved range in the manipulators, you can see the manipulator is kind of angled out on those shoulder joints in this image. Have greater bandwidth through the hull, so if your equipment is sitting outside of on the basket, for example, but you need to see what data it's collecting in real time and make adjustments, you now have a number of different ways to do that, from serial connections to Ethernet connections and the like. The new sphere that was constructed for this upgrade has a depth rating of 6,500 meters. As you might note that in the earlier slides, I mentioned that it has a depth, Alvin can go to a depth of 4,500 meters. There's a few systems left on the sub that are not capable of withstanding 6,500 meters, but those are going to be replaced in the overhaul that's beginning in 2020 and are taking place in 2020. And so when it comes out of that overhaul, Alvin's going to be able to go to 6,500 meters. So if you have science that requires that kind of depth capability, I would say, you know, get those ideas rolling, because this vehicle is going to be able to achieve those depths in fairly short order. And other capabilities are added to the vehicle kind of just in the process of operations, not during overhauls. An example of that is the sub to ship to shore data sharing using an acoustic modem. Alvin, by its nature, is somewhat isolated from the ship, and the Alvin group is developing the capability to share imagery and data through the water column so that folks up on the ship can see what's happening down on the seafloor. A really important aspect of diving, either with Alvin or Jason, is the ability to document what's going on. And we can do that in a number of ways. We collect environmental data with both vehicles. We collect great video with both vehicles. But what really makes all that data useful is that there's expert annotation that goes along with it. And this has been done for many years in Jason. As a dive proceeds, there are watchstanders who are recording what's happening. We're collecting a sample here where we saw a fish there. In Alvin, that's has been done kind of manually through recording your voice or taking notes. But recently we've added a capability for kind of digital documentation during dives. You can see on the left here a screen grab from kind of a web-based app that runs in the sub and is connected with the sub systems so that you can fairly efficiently document what's happening, either with just a button press or with more annotation if you feel you have the time. And so through the dive, either through this tool or what's used in Jason, you're going to build up a database of events that will help you in evaluating or reviewing what happened post-dive. And so on the right, you can see the tool for reviewing that data, where you can scroll through a dive and see frame grabs from the video feeds, along with the information that you as the diver or your colleague as the diver has written down. And this can be really useful for efficiently kind of collating the metadata that you need. For example, when and where did we collect samples, and what are the images of those samples? Or when and where did we see bacterial mats or the like? So this capability is part of the vehicle system now, and should be of use going forward. So if we think about the kind of strengths of the operational strengths of Alvin, we know that Alvin dives during the day, right? It goes in at 8, it comes out at 5, and that's largely due to the fact that you have swimmers who go in and out with the sub to kind of connect lines, as well as, you know, what humans can endure in terms of being in a enclosed sphere for that many hours. Its real strength, I think, is that it's bringing your eyes and your brain down to the seafloor. I talked to lots of the users of all the vehicles, and one of the things that's mentioned really frequently with Alvin is that people feel they're getting the best samples that they can possibly get, making the best observations that they can possibly make, and doing it efficiently, because when we're put into the environment, we're able to assimilate information really quickly. You can imagine if you're looking at a hydrothermal vent, just your eyes and your brain can tell you, look, that's where the hottest fluid's coming out, and that's usually going to be right. The operational pace of Alvin is very regular, and that's well suited for kind of intensive sample processing or rapid return of samples to the surface. If you need to be collecting tube worms every day to run an experiment, Alvin's well suited for doing that, and frees up the night times for ancillary programs, whether it's using an AUV, a camera sled, or CTD cast. And Alvin, because it's untethered, is well suited for working in challenging terrain, dealing with steep walls and rough seafloor and the like. So moving on to ROV Jason. ROV Jason operates at down to 6,500 meters if it's running in a mode with the small inline ROV Medea that acts as kind of a depressor weight for the ROV. Dives are not power limited with Jason, so they're often run for multiple days, spend 2 or 3 days down on the seafloor. Has a similar payload to Alvin, and it maintains this real-time connection between the ship and the seafloor in terms of video, in terms of data, in terms of control of the vehicle. It doesn't have a dedicated support vessel. It can be mobilized on a range of vessels, moderate to ocean class to global class. And similar to Alvin, it has a large number of user selectable video cameras and still cameras. So what you're looking at here is a new launch and recovery system for Jason. And this launch and recovery system has been part of an upgrade to Jason that allows it to run as a single body ROV. So I mentioned that the ROV Medea that runs in between Jason and the ship, and you can see that here on the left, coming down from the crane. You see this kind of blocky vehicle, which is Medea, and tethered to that blocky vehicle is Jason. And the reason for having that there is that that vehicle can absorb the heave of the ship and keep Jason isolated from that heave, so it can maintain its stability on the seafloor. The launch and recovery system is for a single body mode for Jason, and this is a new mode for Jason. And instead of having this depressor weight that isolates the ship motion, the winch itself, which you can see in the background, has heave compensation. So the wire goes in and out of phase with the heave of the ship to keep the vehicle level and stable on the seafloor. So in this mode, Jason operates down to 5,000 meters. And one of the big benefits of this new mode is that it has the capacity to lift a lot. So 4,000 pounds of lift can be accomplished with Jason in single body mode. So in the case that you're deploying large instrumentation or recovering large instrumentation, a single body mode would be a preferable way to do it. In addition, in this mode, Jason operates with swappable skids, so you can change what's on the bottom of the vehicle from latching systems for lifting to increased science bay space for large equipment or tools. So we're taking a look now at the interior of the Jason control vans. This is the control center where the vehicle is operated from. And this, it's great to see these images, and it reflects one of the real strengths of this vehicle, or ROVs in general, which is that it allows for large groups of people to collaborate on the decision making that's needed to do your science on the seafloor. So in this kind of rendering, you can see that in the front row next to all those screens, you'll have a pilot, a navigator, and an engineer. And behind them, you'll have a watch leader and watch standers. And there's lots more space behind them, so it's not uncommon to have even more people come and join during a particular watch. If you have a multidisciplinary program, something like this can be really beneficial. You have the geologists in there picking up rocks. They come across an animal that they've not seen before. If necessary, they can bring in someone and say, is this something unusual and worth sampling or not? So the collaborative nature of this vehicle is one of its real strengths. So I'm going to show you the imaging systems on Jason. They're similar to Alvin in many respects. There's a number of different cameras. As you can imagine, what we record in terms of imagery on the seafloor becomes one of the kind of most valuable data products of any dive. On Jason, in this instance, we have 3 HD video cameras called Mini Zeus cameras. Those are circled in red. A Sulis 4K video and still camera, which is a new addition to the vehicle. 2 deep sea power and light kind of pencil cams. These are cameras that provide more for situational awareness than they do for kind of scientific imaging. In this case, we have a user-supplied still camera on there, and you can see LED lighting arrayed around the vehicle. I'm going to show you some of the video from the Sulis 4K camera coming up next. And I realize that it's not going to come through as beautifully as it does on my screen, but it is gorgeous video. And in addition to being beautiful, it's also really scientifically valuable because you have the capability to get a large-scale overview of the features that you're looking at on the seafloor, but at the same time see enough of the fine detail that you can know whether you're looking at this critter or that critter, or even this rock type or that rock type. So we're going to let that video play. This is from Brothers Volcano and the Kermadec Arc. It's because the imaging is so critical. When you're using these vehicles, it's really important to pay attention to both how to operate the video systems and how to collect good video. And that's not a skill that all of us have, or that especially new users have. And even myself, you get real excited and you start panning that video camera back and forth, and I want to look at that and look at that, and you end up back on the ship and you're like, why didn't I collect at least like 4 seconds of video standing still, in one place? So I recommend kind of being thoughtful about that process of collecting imagery and taking your time to frame shots, think about what's in the frame and what's going to be most useful both for communicating your science and executing your science. All right, so the operational strengths of Jason. Right now, it's the deepest diving vehicle in the facility. So if you have needs to be at more than, in terms of a vehicle like Alvin or Jason, if you need to be more than 4,500 meters, right now Jason is your only option. It has the capacity to collect or to do dives that last a long time. So it's routine to have dives that go for 2 or 3 days. That means you can do things like prolonged sampling that require user control, or such as in some cases large volume pumping. It's well suited for sampling over large areas, and just because it's in the water doesn't mean you can't necessarily do other things. There are activities that you can do concurrently with Jason or during downtime. This vehicle is the only one that's going to let you lift something really heavy off the seafloor, and the collaborative decision making that's enabled by this vehicle is amazing, both within the science party on the ship, but the capability exists to bring that back to shore too, and bring in people who aren't even on the ship into the decision making process.
Hey, Adam.
Yeah.
We have a question from the audience. Jeffrey asks, are any of the cameras or lights in non-visible wavelengths?
Good question, Jeffrey. Not by design. I mean, that capability exists, but it's not a standard capability of the vehicles. So they're all visible light, and the LEDs are all producing visible light. There have certainly been instances where people have put infrared cameras on the vehicle or maybe not infrared, but extremely low light cameras to look for, in one case, the potential that venting fluids are producing light. There's also been examples of putting red lights on the sub to not blind the shrimp that get encountered. So as a standard feature, they're all in visible spectrum. But one of the great things about these vehicles is that if that's a need of yours, then the operations groups will work with you to integrate that capability. It's anytime you're putting something new on the sub, there's resources that are required, and there's engineering time that's required. But that's what our sponsor agencies are there for. So if one writes a proposal and puts in the resources to do it, there's not a whole lot that you can't add to these vehicles. All right, so moving on to AUV Sentry. Sentry operates down to a depth of 6,000 meters and has a top speed of 2.2 knots. Relative to torpedo-shaped AUVs, which is, I would say, the kind of dominant form of AUVs, Sentry has its thrusters on articulating fins, and that gives it the capability to hover near the bottom and work very close to the seafloor, which is unique for AUVs. It has a payload of about 155 pounds, and the endurance has been going up and up, and currently is at 60 hours when transiting at a knot, and 28 hours when transiting at 2 knots, and expected to go up in the future. And that's a product of kind of battery technology advancing really rapidly. Sentry carries an array of sensors, including acoustic sensors like multi-beam, side scan, sub-bottom chirp, imaging sensors, chemical sensors for water chemistry, and geophysical sensors for magnetics. Sentry can be used on its own, but is often used in parallel with Jason, or in serial, and now parallel with Alvin. So the combination of Sentry and these other deep diving vehicles, Jason and Alvin, is a really powerful combination. I'll talk a little bit more about that as we move on. One of the real strengths of this vehicle and its kind of capability that's probably used most often is its high resolution mapping capability. In this image, you're looking at a 1 meter resolution map of the caldera of Havre volcano in the Kermadec Arc. To give you a sense, this area is about 6 kilometers across, and Sentries can't, map this whole thing in one go. So you can see the way it was used in this instance was to conduct a series of dives. In this case, I think 12 dives, and put them all together to create this comprehensive map. And you can see, from this image, we're getting to the point where we are now taking, it's like we're taking photos of, landscapes in the ocean, where the reality is that if you were standing on this map, you couldn't even, see yourself. You would be a tiny little bump. So it's really exciting to see how this vehicle is, bringing on a new phase of how we are able to visualize and look at the seafloor. To give you an example, this is from this mapped area. If you're mapping this area with a ship, you'd see this image on the left. You'd know that there was a bump there on the edge of the caldera. But when you use Sentry, you're going to see every nook and cranny on that bump. And the value of that is incredible for being real efficient with your deep diving vehicle for sampling and observing on the seafloor. To go to spot A, B, and C rather than wending your way around this bump for hours and hours makes your time at sea just that much more efficient. In addition to imaging the seafloor, Sentry is great at looking above and below the seafloor. On the left is an example of some water column chemical sensing done by Sentry. So Sentry made a map of this mound in a program run by NOAA called Deep Search, and then got even nearer to the seafloor and mowed the lawn back and forth using, in this case, an oxidation reduction potential sensor. So this is a sensor that that's great at finding hydrothermal fluids, and you can see hot spots within that. The smaller mapped areas are where fluids are coming out of the seafloor. Sentry has, changed the way that we locate hydrothermal venting, and not just hydrothermal venting, but any source of distinct water, whether that's caused naturally or anthropogenically in the case of the Deepwater Horizon crisis. And then on the right, you see an example of some sub-bottom seismic data collected by Sentry of a gas seep in Guaymas Basin in the Gulf of California. And you can see it does a great job at imaging the sedimentary units, and then this white area in the middle is the area where gas has collected and the seismic energy can't pass through. So Sentry has got this multi-layer kind of ability to image the seafloor in great detail, but then also look at what's happening above the seafloor and below the seafloor, and as such a superb tool for looking at the active processes that we know, extend through that water seafloor interface. The imaging capabilities of Sentry are really good. The image quality doesn't necessarily compare to what you get with Alvin and Sentry, in large part because the vehicle doesn't have the lighting that those other vehicles have. It has a very efficient use of power, and running a whole bunch of lights is not the best for that. But what it does have that the other vehicles don't have is the ability to run structured surveys. And that capability, comes from the need to do that for mapping and for water column surveys. But it's designed to autonomously follow the seafloor at constant altitude and respond to the environment around it, to not run into things or get hung up, but conduct these really structured surveys that are very accurate so that you can go along a transect, move 3 meters to the south and do the transect in the other direction and just move along that way. And here's an example of a photo survey that was conducted at South Hydrate Ridge. You can see in the upper left the kind of extent of that survey, and the area in the big image is from this yellow box. This is 5 meters across, right? The scale bar here. So this image is, probably 30 or so meters across, and to collect an image of the seafloor, photo of the seafloor, you really can't be more than, 3 to 5 meters above it, because light falls off so quickly in the seafloor, is absorbed so quickly that you can't light something when you're further away. So any individual image of the seafloor, is going to be perhaps 5 meters across. So this is a collection of maybe dozens or hundreds of images put together in a mosaic. And once you do that, you can start looking at processes that are reflected in really kind of small scale features. So where are in this case, they're looking at the distribution of bacterial mats and how the macrofauna are interacting with those mats. In the past, you might be able to qualitatively say something about that as you drove by an Alvin or Jason and observed what was happening. But in order to get kind of a quantitative look at it, for things that are, kind of centimeter scale in terms of some of these animals, this is an incredible way to look at the seafloor in a new quantitative way. So the kind of operational strengths of Sentry is high resolution acoustic imaging, these structured surveys for geophysical, geochemical prospecting and for seafloor photography, free of a support vessel, or you free your support vessel for other operations because the vehicle's autonomous, can operate very near the bottom, and in some cases do autonomous sampling as well. And it's a real force multiplier for submersible operations of the type of Jason and Alvin. So I'm going to quickly go through a few use cases for these vehicles. And the first one is kind of general, and it's probably how the vehicles are used most often, and it's just to gain access to the deep sea. Whether you are a biologist, a geologist, a chemist, or a physical oceanographer, whether you want to collect samples or deploy experiments or whatever, these vehicles allow you access to the deep sea. I put up here an article from the Huffington Post about a cruise that just completed. Scientists discovered giant deep sea coral reef off Atlantic coast. That area has been mapped from ships, and then Sentry came in and did some mapping. But when they got down there with Alvin, in this case, they were able to see things that had never been seen before. So it's that access to the deep ocean that these vehicles provide that's the primary use of them. And I think I wanted to make this point because I think it's really important. I talked about the strengths of these vehicles, Alvin and Jason, and there are some differences between the vehicles, but the core capabilities of the vehicles to achieve science objectives are very similar. And so when you're thinking about writing proposals to use these vehicles, it is not at all unusual or even a bad strategy to say, I could use either Alvin or Jason for this. I'll need various amounts of time with Alvin or various amounts of time with Jason, but that's a strategy that might help you kind of get on the schedule to use these vehicles faster when you have that flexibility. And in having used both of them, I've had great success with both, and the distinctions between them kind of fade away for a lot of science operations. Dual vehicle operations, I mentioned this before. When you use Sentry to image an area and then come back to it with Alvin or Jason, you really increase your efficiency for getting to the spots on the seafloor that you need to get to. It's a huge place, the seafloor. Alvin and Jason can be in one tiny spot on it, and when you use a tool like Sentry, you can kind of hone in on the area that you want to work really quickly. Sentry can dive and turn around its data really quickly. So if you're using Alvin, for example, within an hour or two, you can bring Sentry up, get a map, go down in Alvin. Recently, the capability has been developed to use an autonomous tender for Sentry, in this case a wave glider, and that allows you now to dive Alvin and Sentry concurrently. So in the past, you would have to dive Alvin during the day and Sentry at night. Now you can dive them both at the same time. Same is true for Jason. You can dive them both at the same time and really maximize your data collection for every hour that you have at sea. Interacting with marine infrastructure, these vehicles are often used to kind of work with large equipment on the seafloor, whether that's a cabled or autonomous array or autonomous observatory on the seafloor where you need to plug and unplug equipment, whether it's a cork at a IODP drill hole, which is shown in this image here that Julie Huber lent to me from North Pond in 2014, or whether it's just large experiments that you need to interact with on the seafloor. These vehicles, one of the ways the vehicles are used is to interact with that equipment. And then lastly, the vehicles are sometimes used as technology development platforms. So the facility provides support for developing and integrating equipment with the vehicles. You have a new sensor, you can work with the facility to figure out how to connect it so that its data is collected in real time and perhaps controlled with the ROV or the HOV, or in some cases the AUV as well. And so in often what happens when you do that is that you build this tool and the scientific community is like, wow, that's really great. We would like to use that too. And you can propagate it through all the platforms in the facility. An example here is the Super Sampler. This was developed by Chip Breyer, and in the upper left is an example of the Super Sampler being deployed on Jason and then later on Sentry. So you can take your tools and use them in a variety of environments in a variety of ways, whether it's on the seafloor, in the water column in a structured survey, and it's a great use of the vehicles. So how do you get involved? There's lots of new user programs that are run. You guys are part of one right now, which is fantastic, and my appreciation goes out to Dan and Mike and Trish and others who are helping facilitate this. There are onshore workshops that are held annually at AGU and on a less regular basis, run by the facility. And there's other cruise opportunities. So I think the best way to get involved is to start making connections through these opportunities. Get yourself out at sea using these vehicles, and it's going to give you an advantage when it comes time to write your next proposal. And speaking of proposals, it's really important to note that these vehicles can be used at no cost to your proposal, or at least in your budget, when you write a proposal to NSF OCE. The costs are known. They're obviously not trivial, but you're not going to necessarily have sticker shock by having to put how much it costs per day to use Alvin, Jason, or Sentry. And the reason this is done is because the National Science Foundation wants you to use these vehicles. The more these vehicles are used, the better they are. So I can only encourage you to write your proposals to use them. And in some cases, there might be a perception that there's impediment to junior scientists or new users to get access to these vehicles, and I can tell you that is not the case. When you want to use these vehicles, you'll go through project conception, proposal construction, scheduling, execution, and the facility, its job is to help you through all these steps of the process. We can talk to you about your project idea and whether it makes sense, and whether, as Jeffrey mentioned, whether you need to put in resources to develop infrared cameras to be used on the vehicle. We can help you devise field plans that are both realistic and accomplishable, and we can even connect you with folks who can help you do that, and we can advise you on what's a viable support vessel, what weather window do you want to pay attention to, and even your vehicle choice if it impacts your ease of scheduling. And then at sea, I can't say enough about the operations teams and how hard they work to help you achieve your objectives. So just to wrap up, the National Deep Submergence Facility operates these three unique and complementary capabilities that provide you with access to most of the seafloor and water column. Anyone is welcome to use these vehicles. It doesn't matter your discipline or your experience level. And one of the best ways to do that, or to help you do that, is to get in touch with us early and often so that we can assist you in getting access to these vehicles. So you see on the bottom of the screen here, myself as the Chief Scientist for Deep Submergence, Matt Heinz, the Jason Operations or the Program Manager, Bruce Strickroth, the Alvin Program Manager, and Sean Kelly, the Sentry Program Manager. You see numbers, you see emails, get in touch with them, and also I should note there's an error on Sean's email address, which I have to correct, but that's it. Get in touch with them. So thank you for listening, and I'm happy to take any questions. I know we've gone over our time or up to our time here, but I'm happy to stick around and take questions.
Okay, hey, Eric here with AGU, and while we wait for questions to come in, just a reminder that the next webinar in this series will be held on Friday, October 29th at 2 p.m., and you can register for that webinar by going to webinars.agu.org, and you'll see the link to register there. And it's on life and safety at sea. We'll just give it a couple more minutes in case there's any questions for anyone. I look so sad in my little AGU. I'm cramped in a little phone booth. Okay, we got some questions coming in. Let's see here. So Tina asks, how many push cores can Jason take max?
That's a good question, Tina. I don't know the number, but I can estimate for you. I would say that if you fully loaded the basket with push cores, you could probably take 40 to 50. The one thing to pay attention to with that is that while the acrylic tubes of the push cores are, fairly cheap and easy to make, if you're going to collect that many push cores, you would probably have to bring your own. And the handles that are provided for those push cores, so that's a titanium T-handle with a stopper that fits in the top of your tube, they may not have 40 or 50 of those. So that would be a scenario where you would want to talk to them about that. And then the other thing I would mention is that's a lot of sample processing that you are going to set yourself up for if you collect 50 push cores on a dive. But if that's what you need for your science, then absolutely, it can be done.
Okay, and Masako asks if the webinar was recorded. I forgot to mention that a second ago, but yes, we are recording the webinar, and everyone who attended will be sent a link, I think in 2 days, an automatic webinar email from GoToWebinar that will have a recording link. And we'll also post the recording link on the AGU webinars page. And if you have a friend or colleague who wanted to attend but couldn't make it today, but they've registered, they will also be sent the recording link. Okay. Oh, we got one more from Chelsea. After we make arrangements with you, do we have to tag you as a person of support on our NSF proposal?
No, you absolutely not. No, these fall more into the area of kind of conversations with your colleagues to help you devise the proposal. We don't need to be listed on the proposal in any way other than when you're requesting a ship and a vehicle, you definitely have to check the boxes that say, I want to use this or that vehicle. But no, this is just the goal of the facility is to get these vehicles used as much as possible. And so it's in our interest to help you develop the best program that you can.
Okay. I'm not seeing any more questions coming in. I guess, Adam, folks have your contact info if they want to reach out to you. But thanks so much.
All right. Thanks, everybody.
Have a good one.
Eric, what do I do now?
Hold tight.